Right, question 7, looking at resistance of a thermistor. So first thing I want you to do is to draw the circuit symbol for a thermistor, which is a resistor with our line across like that. The student uses voltmeters and ammeter readings to find out the resistance at each temperature. One set of readings is shown here at 80 degrees, and they want us to calculate the resistance. First of all, though, they want an equation linking voltage, resistance and current, and what we're going to come up with is V equals IR. If you're going to use symbols, then you want to define them as well, so underneath you need to make sure that you've written, for example, V is voltage, or you could just write the whole thing out in words. Show that the resistance of the thermistor at 80 degrees is about 5,000 ohms. Well, resistance, if we rearrange the equation, is voltage over current. Voltage 13.2, current 2.60. But we've got to remember that this is in milliamps, okay? Now milliamps means that basically we have to divide by 1,000, okay? It's the same as timesing it by 10 to the minus 3, but you could equally just take 2.60 and divide it by 1,000. And the answer that we're going to get out of this then is 5077 ohms. Another student takes measurements for two more components, A and B. A, the resistance goes down as the temperature goes up. B, the resistance goes up as the temperature goes up. Now compare the results for component A and component. Now there's all kinds of different ways that we can compare the results for A and B. Let's just put them together a minute. Now, probably the most simple thing to say is what I said initially, that as the temperature goes up with A, the resistance goes down, while as the temperature goes up with B, the resistance goes up. Okay? We can then add to that one of these could potentially be a thermistor, okay? And we're looking here at A. It's the fact that A has a resistance that decreases as the temperature increases. So that's a possibility here, while for B it's definitely not a possibility. The other things that we can write, well, we can say with component B the resistance stays pretty much constant up to just under 60 degrees, okay? While if we're looking at A, we can say that after about 80 degrees the resistance stays roughly constant then. With A, we can say that to begin with, at high temperatures there's a high gradient. That means the resistance drops quickly per degree change in temperature, while towards the end the gradient is going towards 0, and that's telling me that the resistance isn't really changing at all as the temperature changes. You could say the opposite about B. You could say to begin with the gradient is 0, therefore as you change the temperature by 1 degree you get 0 change in resistance, but then as the line gets steeper and steeper we can say that there's a bigger change in resistance per change in temperature of 1 degree. For question 8, we'll look at a caravan being pulled by a car. State the equation linking work done, force and distance. Well, work done is equal to force times distance moved in the direction of the force. Calculate the work done by the car on the caravan. Well, the work done is equal to the resultant force, which is 170, times the distance travelled, pulled by 110, and that gives 1,870 joules. Okay. How much energy is transferred to the caravan? Well, if we assume that it's a 100% efficient process, then we can say that the same amount of energy is going to be transferred, because work done is energy. If you do 1,870 joules of work on something, then it should gain 1,870. We are making an assumption when we do that, though. We're assuming that there's no energy losses through friction or air resistance or any processes like that. And the mass of the car is 1650, and the caravan is 950. State the equation that links kinetic energy, mass and velocity. Well, KE is equal to half mv squared, where m is mass, v is velocity. Calculate the kinetic energy when the car and the caravan travel together at a constant speed of 23 meters per second. Well, the combined mass is going to be 2,600 kilograms. Okay, so we're going to times that by the square of the speed, which is 23, and then we're going to divide that by 2, and that gives 688,000 joules of kinetic energy. The caravan is removed and the car makes a return journey without it. Without the caravan, the car has a greater acceleration and uses less fuel. Can we explain the... with or without the caravan, the car is still going to be able to have the same driving force. So in this case, the driving force is unchanged, because the caravan doesn't contribute towards the driving force. What we also know is that F equals ma, okay? And therefore the acceleration is dependent on two factors, the force and the mass, okay? And if we look at that, the acceleration is inversely proportional to the mass as long as the force is constant, okay? Now in this case we have less mass because we're no longer pulling the caravan, so if the mass is lower, okay, and it's on the bottom of that equation, then the acceleration will be higher. Okay. You could also use arguments about there's reduced air resistance because we're no longer got the surface area of the caravan included, and the car's surface area is much less. Alright, question 9. A student plans to measure the thickness of a sheet of paper with a ruler. Explain why it's difficult to measure the thickness of a single piece of paper with a ruler. Well, it all comes down to what we call the resolution of the ruler. Okay? Now, the resolution of a ruler is going to be a millimetre, or maybe you might say half a millimetre, but the scales on the ruler is 1 millimetre, and therefore you could probably distinguish between halfway between that scale. Okay? When I say resolution, I really mean the smallest division of an instrument that we can measure to. Okay? Now, if the resolution of the ruler is 0.5 millimetre, then it's not possible for us to get an accurate measurement of anything less than that. Okay? So the thickness of a piece of paper is less than the resolution. And any measuring device, if it wants to be used properly, needs to have a resolution that is greater than the measurement you're trying to take. Now the student gets around this by using multiple pieces of paper. So he puts 400 sheets on the table, and together the 400 sheets are 4.1 centimetres, okay, which is 41 millimetres. So how much does each piece of paper, what's the thickness of each? Well, we're going to divide that by 100, okay, and we're in the region, we're going to divide that by 400 because we've got 400 sheets. We're going to be in the region of 1/10 of a millimetre, okay. Now this is why we're unable to measure it with a ruler, because a ruler at best is going to have a resolution of half a millimetre. Anything smaller than that we're not going to be able. Now I then asked to give 2 reasons why the value for the thickness of the pile might be inaccurate. Well, if we look at the diagram, okay, can we be certain that the ruler is perpendicular to the floor? I mean, is this definitely a right angle here? If it's not, then instead of the ruler going up at 90 degrees to the surface, we could have the ruler going up at an angle, I'm exaggerating here, that's not 90 degrees, and therefore the height that we might think of as 4.1 centimetres along here is actually going to be much less than that. Okay, it's going to be this side of the triangle. So that's one reason that maybe the ruler is not perpendicular to the surface. Another one might be a zero error. Okay, does the ruler start exactly at 0? Okay, and often you see rulers where there's a small bit of plastic between the edge of the ruler and the 0. So that's another reason why it may not be. The student folds a sheet of paper to make a paper aeroplane and throws the paper aeroplane, and it flies at a constant velocity. Explain why the forces on the paper airplane must be balanced. Well, Newton's first law says that if any object is stationary or travels at a constant velocity, then there must be 0 resultant force. Okay? And 0 resultant force means that the forces must be balanced. In this case, we're looking at the air resistance. Well, there can't really be any air resistance in this case because there's no forward force, and there'll be no resistive force either. Going on to the next part, the diagram shows the paper airplane as it moves at a constant velocity towards the right and slightly downwards. Add the following forces to the diagram. Okay, they want to know the direction, so we're going to be showing vector arrows. So the weight is always going to act on the centre of gravity downwards. Okay. Now, in the opposite direction, we're going to have the lift. If it's going slightly downwards though, then we've got to make sure that we show the weight as being greater than the lift. Okay, so this arrow here is going to be bigger. Now, if it's moving to the right, then the drag is going to be in this direction here. Okay. Now, once the paper airplane has left the hand, there is going to be no force in this forward direction. Okay, so the only way it can really go at a constant velocity is if there is no drag here as well. So I don't really like that question because on the mark scheme they ask for the drag to be shown to the left. Really what we're going to have is, because it's moving in the direction which is slightly downwards, the drag is going to go this way too, and it's going to be a component of the weight that's going to balance the drag, but we don't really need to get into that when we answer it. As it flies, the paper airplane loses gravitational potential energy. What happens to this gravitational potential energy? Well, there's going to be a conversion of GPE into KE, okay, kinetic energy. So it's going to increase its speed as it gets closer to the ground. So an airplane takes 2 minutes to travel the short distance between airports on 2 islands. The graph shows how it takes off, flies across the sea, and then lands on another island. Use the graph to answer the following questions. Calculate the value of the constant speed. Well, the constant speed is on this axis, so constant speed is this section here, and it looks to me to be roughly halfway between 40 and 45. I'm going to say 42.5 then. Right, next one. Calculate the acceleration of the aeroplane at the start of the journey and give the unit. Now, acceleration at the start of the journey, we're looking at this section here. That's a speed time graph, and acceleration is the gradient.
So the kind of the characteristics of the question are that once you should be
Will it have just died, or does it keep stuff?
Depends.
So acceleration is the gradient of a speed time graph. So if we do our rise over run here, we're at about 42.5 and the run is about 15. So acceleration 42 divided by 15, and if I just do that on a calculator in a minute, that's 2.83, so 2.8, and the units are meters per second squared. It then asks what's the total distance that the aeroplane travels. Again, we're looking at the speed time graph. If we want distance, then we're looking at the area under. So we've got this area here of a triangle, got this area here of a triangle, and then we've got the rectangle in between. So for the first triangle, we're looking at half base times height, which is half times 15 times the height, which is 42.5. For the middle rectangle, where we're going from 15 to 95, so that's 80, and we're timesing that by the height, which is 42.5. And then for the final one, we're going from 95 to 120, so it's going for half 25 times 42.5. So these are my 3 different distances. Okay, this